Hello guys, good morning. I want us to start with something that most of us may be familiar with, which is, I believe a lot of people are familiar with what is called the production possibility frontier. If you're an undergraduate student, it's possible that you have come across this before in one way or the other, some form of economics course. So we have a production possibility frontier where you have a combination of labor and capital that you will use to produce some level of economic good over this frontier. So you have some portions here. You have other areas here. And you have the areas on the curve as well. Remember from your background, if you are going to produce, you are going to use resources which are limited from the basic economic idea of scarcity. So you want to produce as much as you want, but you're only constrained by how much of labor and capital you have in this situation. So you are going to either be inside A, let's say this is A, this is B, or you are on the line, which is, let's say, C. Okay. So the resources that you have, which is limited, is bounded by this line, this frontier. So this is a frontier. And that's your scarcity. So you can attain all the portions in A, all the portions in A. You can produce anything inside this and on that. But you cannot go into the region C because your resources are limited. You cannot get there. Okay. But you can produce from any region between A and B. But the best that you should do is to be on the frontier. If you are on it, then you are making the best use of the limited resources you have, the bank capital. If you are in A, you are inefficient. You are wasting resources. You could be on C, but you're operating in A. So you are being inefficient. You are not operating at optimum. Okay. However, you cannot get to B because your resources cannot get you there. So you cannot attain. It's unattainable region. But if you are on C, you are optimal or efficient, or you are operating at best. And all of that is optimization. So if this is production, so it's something that you want more of, all things being equal. So you want to optimize your use of resources, labor, and capital. So that's what we want to look at today, optimization. And optimization can be, so it's in two areas. So optimize and go up where you are maximizing, where it is best. But sometimes you have to minimize as to get the best as well. And we know that you maximize what is desirable for you and you minimize what is undesirable. So things that such as costs, waste, or items that are undesirable, you want to minimize them as much as possible. So the list of it is what is best. But if it is something that you desire, your sales, revenue, profit, items that you have to produce, you want the best. In that case, you want the most of it. So those are the two scenarios. The middle part where you are making just about enough, which we call satisficing, is not really important. You are either maximizing or minimizing. So you want to look at the mathematical basis around it. Not that we are going to do mathematics, just go through some ways of looking at it and we implement it in R. So in terms of quantitative decision making, we cannot actually, it will be strange if we do not look at linear programming. So you have an objective. I prefer the red ink. An objective like the possibility frontier, labor capital, to be on the line to, in this case, maximize. You want to achieve the best of the combination of labor and capital. If you achieve the best of the combination of labor and capital, you're going to get a particular outcome. That's your objective. But you are subject to constraints. And the constraints is what limits you to the frontier. So you may have a situation like maybe you have a production function, which is if you have the Cobb-Douglas production function, which is so the Cobb-Douglas production function typically looks like as a P is equal to AK and alpha minus beta, where you have alpha being certain numbers and beta being certain numbers, where you have your constraints, labor maybe is less than a certain value, capital is also maybe greater than a certain amount, and then you have an additional constraint if you produce the constraint where labor and capital should both be positive or non-negative. Okay. Now, if you look at this function, it can be linear or not, depending on the values of alpha and beta. So if you have alpha to be, say, 3 and beta to be, say, 1, then your problem is not a linear problem because you're going to have L be of squared and A. But if you have alpha to be, say, 2 in this situation, then you come back to a linear relationship in powers of 1. So your optimization may be a linear relationship or it may be a non-linear scenario. So you can have a linear problem or a non-linear problem. It arises in different situations. In this session, we are looking at the linear scenario. So this is what we have been talking about so far. So we want to look at the linear relationship. The linear relationship means that we can only solve them using linear programming techniques. The basic ones or the common ones are the graphical method. So, and that is very basic because manually you can only do and make a 2 Cartesian plot. So what will happen is that when you have your linear programming formulated in X and Y, you can write your constraints in the form of equations instead of inequalities. Then you can plot them. However, maybe they are 3 or 4. So you can plot them with 1. Maybe this will be like 1. That will be a constraint. Then you have to block out the area that you cannot achieve depending on the constraint. Then maybe you have another line 2. Then block that side as well. And realize that you cannot, if your situation, which most of the case you have non-negativity constraints, you are going to be, this is 0, so you are not going to be able to come down here or there. So if your constraints are 2, or maybe there's another constraint lines 3, you block out this one as well. So what you have, you realize that you have your constraint set up for you. So you are bounded within here, there, and there. So if you say this is your A, B, C, D, and E. You have how many corners? You have 5 corners of this, say, polygon that you have created based on your linear programming situation. What you can do is that within this space, there's an infinite number of combinations of X and Y, or maybe label and capital, that will give you different levels of output. But you cannot evaluate, or you cannot find all those infinite numbers. So what you can do is to evaluate your objective function at the corners. So this will be a point, maybe 1, 2. This is also another point, 2, 3. That point, maybe 1, 4, 2. Another point, 2, maybe 0, 2. And this will be 0, 0. So you are going to evaluate your objective function for all these 5 corners. So each one of them will give you a certain amount or number. Now, earlier, we didn't care whether it was optimization or minimization, but they are also, whether it's optimization or minimization, it affects how the constraints are given. But once you are making the graph, it does not really matter. You're just following the constraints. Okay? So at this point, then once you evaluate through the corners, you are going to check whether you are minimizing or you are maximizing. So if you are maximizing, you are going to look for the 5 possibilities that gives you the highest number. That will be your solution. That will be your optimal solution. And that will be achieved at a particular corner. So whether A or B or C. So if it's B, it means that 1 unit of X and 2 units of Y is what is going to give you the best outcome. With minimization, you go through all the evaluated objective function and look for the least amount or the least number. That will be your optimal solution. And whichever points gave you that solution, that will be your numbers. So that's when you have 2 variables. But another issue is that you run the risk of not being precise in your answer because your graph is not to scale. But if you have more than 2 variables, then you cannot use this situation. There are other ways that you can do that. One of them is the simultaneous equation approach. So you can run series of simultaneous equations, solutions, and evaluate them for the best answer. The next one, which is mostly used, is the Simplex approach. And that's basically algebraic evaluation or manipulation of your problem. So you convert your problem to a matrix and you do row operations based on certain conditions. So one of the conditions is that if you are maximizing, then when you do all your elementary row operations, your objective row should have only negative or 0 values, only negative or 0. When you are able to get that in the objective row, then you have arrived. And you may have done that through several iterations or several operations that you have to get there. If you are minimizing, then you are looking for either 0 or positive only. But how do you do the elementary row operations, you have to choose a pivot row and a pivot column, and you start the operation from there. So your typical pivot column or row will be, your pivot row will be the row with the highest positive number if you are doing maximization, because you want everything to be negative or zero. So you pick the highest positive number and you start the operation from there. When you finish the first operation, you go and look for the next positive number, which is highest. You go through that until you have reduced all of them to either zero or negative, then you have arrived. Then the minimization is the reverse. Okay. And most softwares, when you use Excel, Lingo, I think they all use the Simplex approach to do it, and you can have several variables in the problem, and that will work fine. So I'm just giving you the basis. We are not going to go into that one. We'll try and look at different situations and evaluate them. So there are also nonlinear programming scenarios, as I mentioned. So when your objective function or your constraints are in powers, or that is the powers that is different from one, then that's a nonlinear situation. And the nonlinear techniques that may be used are a number of them. The Kuhn-Tucker conditions, and you also have the method of approximation. Yeah, I think there's an error here. Method of approximation. So they are nonlinear situations. Let's take this example. If you look at this example, maybe you can take a minute to read it. So you realize this is a portfolio. So investor has this amount of money with the potential to invest in two investment options, I and J. I mean, two, J1 and 2. And there are return expectations. There are also risk expectations. And as you can see, risk is it's a squared quantity, so the risk is given there. And so what will be the combinations of 1 and 2 that they should do to get the best outcome? Okay. So you can maximize the situation like this here. So you realize that this part of the situation is nonlinear because of the squares here. And this part is linear. So what you can do is check. So theta, if theta is equal to 0, then the whole second part goes away, and you are left with a linear relationship to deal with. And you realize that the constraints are also in linear form. Okay. But if beta is not equal to 0, if it is any number, then that is a nonlinear problem. But it's a maximization problem. Okay. So when you read the situation, you may not be told specifically this maximization, but you can deduce whether you need to maximize or to minimize. It's another situation here, which is a minimization problem. So if you look at it, acquisition cost per ton for each raw material. Okay, so you have your demand and you have your unit cost. Once you're dealing with cost, you want to minimize. So in addition to the purchase and storage cost, the transportation costs have to be considered in order to get the minimized or the least amount of cost for production. So that is a minimization problem. Okay. Now let's take some examples that we are going to go through. So we have one situation here. We are saying that it's a small enterprise that produces two things. We have dresses and we have pair of trousers. So they use resources, and here we have two resources that they use. The resource that they use is time, actually one resource, time. And the time is split between cutting and stitching. So what you may want to do, you can start with saying that let X be dresses and Y be trousers. Okay. So you are going to have trousers and dresses. Okay, so we put that down. You are saying the prof. Okay, let's look at let's finish reading the top. To make trousers requires 15 minutes. 15 minutes of cutting and 0.5 hours of stitching. So you are going to have cutting somewhere here and you are going to have stitching somewhere here. So 15 hours of cutting for trousers. So 15 for trousers and another what? I think we skipped one. Yes, 0.5 hours for, okay, let's start from top. 0.5 hours for dresses. So 0.5 for dresses, and we have 0.5 20 minutes for stitching. Okay, so that's for dresses and also 20 minutes. We'll convert them so that they are in minutes or they are in hours. Okay, we'll do that when we get down here. So that's for trousers. When we go to, that's for dresses. When we go to trousers, we have 15 minutes. 15 minutes for cutting and 0.5 hours for stitching. 0.5 hours. So I think we should change everything to minutes or everything to hours so that it will be easier. So 0.5 hours, so that's 0.5. And 15 minutes is a quarter, right? So 0.25. And here, 20 minutes is 1/4. 20 minutes is 1/4, no, 1/3, 1/3. And the other one was what? The 0.5 hours, which is fine. So we leave that one down. Now, we are told that the business operates a maximum of 8 hours. That means each of these cannot go beyond 8 hours. Okay. So that will complete your constraints. And we can add that X and Y should both be positive. So trousers and dresses should be positive. But what are we to do? We have profit for dresses. So profit for dresses is going to be 40 and profit for trousers is 50. And this is our objective function. Objective. And we want to optimize that. Now, this is profit, so obviously you want to maximize. However, you can always look at the requirement. You have to determine then how many dresses and trousers should be made to maximize profit. And what is this profit? So that's the situation. And we have formulated that here, which you want to do that through what? Through R. So that's, so use T and D here, the same as X and Y, and the constraints are given. Want to use the LP solve package for this situation. But before we go into R, we want to look at another situation, which is minimization. So here we realize that there are also two food items, X and Y. And there are three different kinds of nutrients. So we have protein, we have carbohydrates, and we have fat. So our constraints will be around those three nutrients. And it says that each kilogram of X, so X will take 1 protein, uh, two, two carbohydrates, and 1 fat. So that's for X. Then if you take Y will take 1 protein, 1 unit of carbohydrate, and 1 unit of fat. Okay, so you note that one, you can put them in a table if you like. Then we are saying the two items together must provide at least is so greater than or equal to 7 units of protein, 10 at least 10 units of carbohydrate. That's also greater than or equal to, and no more than. So that now changes all of a sudden to a less than or equal to of fat. Then you have costs. So the cost of X is 2,000 and the cost of Y is 8,000. And because these are costs, we want to minimize. So when you look at the situation, you should be able to formulate the linear programming problem and go ahead to solve it. So this is the optimization. It should be X. Yeah, X. So this is the formulation, and we want to solve that one as well. We are not using external data today, but let me set working directory so that it will be easier for me to locate my script. Instead of before that, let me remove the annotation from my. Never mind. I'll close it and not save. So let's open. You have to look at the. Let's open the slide on one side. So we should be going back to look at the formulation. So we can do the maximization first, the first example. So first of all, as always, we get our package to work. So do that. Then we set our objective function. So this is how it works. You are going to set the objective function as a matrix or as a column vector. So it was 40t or 40x plus 50y. So this is the 40 and this is the 50. That's very important because how you set this one, how you set your objective function will correspond to the number of columns you choose here. So on line 7, you see number of column equal to 2 because we are looking at two decision variables, x and y. Okay. Now we had two constraints as well. So the two constraints, it was 0.5 x plus 0.25 y. So those are the first two. Yeah. Then there was another one, 1/3 of x and 1/2 of y. So that is this one. So those are our constraints. Now, what you can also do is that if you want to use your number of rows here, then they should correspond to the constraints, not the decision variables. So if we put number of rows is 3 or 4, depending on the number of constraints we have, then that's fine. Okay. So you can either do this for the constraints or do number of columns for the decision variables. That's very important. If you don't do that, your algorithm will fail to work because the rows and the columns will not match. Then there's the direction. So what is the inequality for the constraints? It was less than or equal to for both of them. So we write them in the quotation as they are. And there were two constraints, so we should have two of them. On the right-hand side, was also 8. So we specify that as well. So we can also run the constraints. And as I said, you can do that, the column or the row, they will be the same thing. So that is also done. Note that the non-negativity constraints are default, so we don't have to bother with them. Now, this is how the function works. The function works with LP. So the LP is a function which takes the nature of the optimization, whether it's a maximization or a minimization. So that should be in quotation max. Then it follows by your objective function, your constraints, the direction of the constraints, and the right-hand side of the constraint. And there's an additional function which computes sensitivities. We may not go into that, but when you have finished solving your linear programming problem, what are the allowable changes to the constraints or to the decision variables that you can make? So those can tell you how low or how high you can go to remain feasible in your solution. So that is there. You can run that one. So that runs your linear programming problem for you. So we have no errors. That means we are successful. So we may print the solution. So the objective, the maximum profit is $880. But how do we arrive at that? How do we get 880? We can get that by picking L.max dollar solution. That will show us how many of X and how many of Y we should produce in order to get that 880. So we need to produce 12 dresses and 8 pairs of trousers to achieve a maximum profit of $880. So you can see if you multiply let's the objective. If you multiply 12 by 40 and you multiply 50 by 8, the sum should give you 880. So based on the constraints that you have, this is the best that you can do. So as a decision, if you're a manager and you need to take a managerial decision, this is the best combination of produce, the pairs of trousers and dresses that you need to produce to make the best of profit subject to the constraints you have. That is for the maximization. We can do that for the minimization as well. So we have our objective function. There are constraints. Remember we had x plus y. Another one was 2x plus y. And the last one was x plus y. Okay. So 3 constraints. So but when you come here, we are doing number of columns. So we are referring to the decision variables x and y, which is 2. But we can use the number of rows to refer to the constraints, which is 3 constraints here. So either of them will work. We take note of the inequalities. The first 2 were greater than or equal to, and the last one was less than or equal to. Sorry. And the right-hand side, we have 7, we have 10, and we had 8. Okay, so let's run them. They look good all the way here. But now we are minimizing. Okay. After that, we'll change it to maximize and see what will happen. We are minimizing for objective function, our constraints, inequalities, and right-hand side, as well as looking for sensitivity computations. So let's run our optimization. Everything looks good. And what do we have? What is our optimal cost reduction? $14,000. We can achieve that 14,000 by producing 7 units to I think 7 lunch boxes of the first lunch and nothing at all of the second. So don't produce any of Y. Put all the resources into the production of X, and that will minimize your cost for you to down to $14,000. So that's the whole idea of linear program. If you've done that in Excel before using solver, you get the same thing. If you do it manually through the Simplex computation, you get the same thing. If you use the Lingo software, you get the same thing.